Welcome to this walkthrough of problem number 1091, shortest path in binary matrix. In this session, we'll explore how to solve this problem efficiently, step by step. Get ready to dive into an interesting algorithmic challenge. In this problem, we are tasked with finding the shortest path in an nxn binary matrix, called grid. Here, each cell in the matrix is either a 0, representing an empty cell that can be traversed, or a 1, representing an obstacle that cannot be crossed. The goal is to determine the minimum number of steps required to move from the top left corner, at position 0, 0, to the bottom right corner, at position n1, n1. A key condition is that the path can only pass through cells containing 0. Additionally, movement between cells is flexible, as you can traverse in any of the 8 possible directions, vertically, horizontally, or diagonally. If no valid path exists, you should return -1 as the output. The length of the path is calculated as the total number of steps taken, where moving from one cell to another counts as one step. Let's look at an example to better understand the problem. In the first example, the input grid is a 2 by 2 matrix, 0, 1, 1, 0. The shortest clear path from the starting cell, 0, 0, to the ending cell, 1, 1, is of length 2. Starting at 0, 0, we can move diagonally to 1, 1, and since each movement counts as one step, the total length of the path is 2. This illustrates that diagonal movement is allowed and can contribute to finding the shortest path. Now, consider a larger example where the input grid is a 3 by 3 matrix, 0, 0, 0, 1, 1, 0, 1, 1, 0. Here, the shortest path from 0, 0 to 2, 2 has a length of 4. The path can start at 0, 0, then move right to 0, 1, and again right to 0, 2. From there, we can move diagonally down to 1, 2, and finally, diagonally down again to reach 2, 2. This example demonstrates how a combination of horizontal, vertical, and diagonal moves can be used to navigate the grid efficiently. Continuing with the explanation, the sequence of moves for the second example is as follows. Start at 0, 0, move right to 0, 1, then right again to 0, 2. After that, move diagonally down to 1, 2, and finally, diagonally down again to reach 2, 2. These moves cover all cells in the shortest path, and the total length is 4. Now, let's examine another scenario where no clear path exists. In the third example, the input grid is 1, 0, 0, 1, 1, 0, 1, 1, 0. In this third example, the starting cell, 0, 0, contains an obstacle, represented by the value 1. Since the path must begin at 0, 0, it is impossible to proceed, and there is no way to reach the bottom right corner, 2, 2. Therefore, the output for this case is -1, indicating that no valid path exists. Finally, the problem comes with a few important constraints and edge cases to keep in mind. The grid is always square, meaning its dimensions are nxn, with n ranging from 1 to 100. If either the starting cell, 0, 0, or the ending cell, n1, n1, contains a 1, the output must be -1 because the path cannot start or end on an obstacle. For a grid of size 1 by 1 with a 0 at 0, 0, the output should be 1, as the start and end are the same. For large grids with no obstacles, the shortest path would simply correspond to the Manhattan distance. On the other hand, completely blocked grids should return -1, as no path is possible in such cases. To tackle the problem of finding the shortest path in a binary matrix, one approach we might consider is the brute force method. The intuition here is simple. Start at the top left corner of the grid, at cell 0, 0, and explore every possible path to the bottom right corner, or cell n1, n1. Since movement is allowed in 8 directions, this means trying all combinations of steps recursively or iteratively, while avoiding obstacles, which are cells marked as 1. However, there are some critical observations about this approach. First, it requires exploring every possible path, which can be extremely computationally expensive. For larger grids, the number of potential paths grows exponentially, making the brute force method infeasible. In terms of complexity, the time required is 8n*n in the worst case, as it involves trying all possible paths. Space complexity is n*n, primarily due to the recursion stack or the need to maintain a visited matrix. While this method is simple to implement, Its inefficiency for larger grids and lack of focus on the shortest path make it less practical for this problem. A more efficient strategy is to use breadth-first search, or BFS. BFS is particularly well suited to shortest path problems in unweighted graphs, and here the grid can be treated as such a graph. Each cell acts as a node connected to its valid neighbors. Starting from cell 0, BFS explores all neighboring cells level by level, ensuring that when we first reach the target cell at n1, it is along the shortest path. There are several key aspects to note. BFS guarantees the shortest path due to its level order traversal. To implement this, we use a queue to store the current cell along with its associated path length. Additionally, a visited matrix is critical to ensure that each cell is processed only once, avoiding unnecessary reprocessing. When considering complexity, BFS processes each of the n-squared cells at most once, leading to a time complexity of O(n)². Space complexity is also O(n)², accounting for both the visited matrix and the queue. This approach is efficient, scalable, and balances computational resources effectively, making it a strong candidate for solving this problem. Another approach we could consider is the A** search algorithm, which is an informed search method. A* uses a heuristic function to prioritize nodes that appear closer to the goal, potentially reducing the number of nodes explored. For this problem, we can use either the Euclidean or Manhattan distance to estimate the cost from any given cell to the target cell at n1. This heuristic allows A** to focus its search on paths that seem more promising. However, there are key considerations with this method. While A** can reduce the number of nodes visited compared to BFS, its effectiveness depends heavily on the heuristic design. A poorly chosen heuristic could compromise both correctness and efficiency. In terms of complexity, the time requirement is O(n)² log n, due to the overhead of managing a priority queue. Space complexity remains O(n)², accounting for the visited matrix and the priority queue. While A** has its advantages, such as potentially faster search for large grids, it is more complex to implement than BFS and may not provide significant performance gains for smaller or moderately sized grids. Among the strategies discussed, breadth-first search is the chosen solution for this problem. BFS is optimal for unweighted grids, as it guarantees finding the shortest path while maintaining simplicity in implementation. Unlike A**, it avoids the added complexity of managing a heuristic and a priority queue. Brute force, on the other hand, is computationally infeasible for large grids, leaving BFS as the clear choice. The implementation of BFS involves a few key steps. First, an edge case check ensures that if the start cell 0, or the end cell n1 is blocked, the function immediately returns -1. Next, the BFS process begins by initializing a queue with the starting cell and its initial path length, typically represented as 001. A visited matrix is used to track which cells have already been processed, preventing redundant work. During the traversal, the current cell is dequeued, and its 8 potential neighbors are explored. For each valid neighbor, the algorithm marks it as visited and enqueues it with an increment path length. The search terminates as soon as the target cell is reached, returning the path length. If the queue is exhausted and the target cell is not reached, the algorithm returns -1. This systematic approach ensures both efficiency and correctness. Although A** could also solve the problem, it introduces unnecessary overhead for this specific case. Maintaining a priority queue and computing heuristic values adds complexity without significant benefit, since BFS already guarantees the shortest path in an unweighted grid. The complexity analysis further supports this choice. BFS has a time complexity of O(n)², as each cell is processed once, and a space complexity of O(n)², accounting for both the visited matrix and the queue. These metrics are optimal for this problem, given the constraints. In conclusion, BFS is the most efficient and straightforward solution to the shortest path in binary matrix problem. It strikes the right balance between time and space complexity, ensures correctness, and is relatively simple to implement, making it the ideal choice for tackling this challenge. In this problem, we are tasked with finding the shortest path in an nxn grid where cells can either be open spaces, represented by 0, or obstacles, represented by 1. The goal is to start at the top left corner, 0, and reach the bottom right corner, N1, using valid moves. Movement is allowed in 8 directions, including diagonals. If there's no valid path, the output should be -1. The first step is to validate the input. If the grid is empty or its size is 0, we immediately return -1. Similarly, if the starting cell, 0 is 0, or the target cell, N1, is blocked, meaning it contains A1, we know it's impossible to find a path, so we return -1. Once the input is validated, we use breadth first search, or BFS, to solve this problem. BFS is particularly suited for finding the shortest path in unweighted graphs, as it explores all possible paths layer by layer, guaranteeing that the first time it reaches the target, it has found the shortest route. In our grid, each cell acts as a node, and the valid movements between cells represent edges. To implement BFS, we need 3 main components. First, we use a queue to manage the cells to be processed, where each entry includes the cell's coordinates and the path length required to reach it. We initialize the queue with the starting cell, 0, 0, and a path length of 1. Second, we maintain a visited set to track cells that have already been processed, preventing cycles and redundant work. Finally, we define an array of direction movements, representing all 8 possible directions as dx, dy pairs, to simplify the traversal logic. To execute the BFS, we process cells layer by layer. While the queue is not empty, we dequeue the front element, which includes the current cell coordinates and the path length. If this cell is the target, N1, we return the path length, as it guarantees the shortest path. Otherwise, for each direction in our predefined direction array, we calculate the next cell, NX, New York, by adding the direction offsets to the current cell's coordinates. We then check if the next cell is within the grid boundaries, is not an obstacle, and hasn't already been visited. If all these conditions are met, we mark the cell as visited and enqueue it, including the updated path length. This process continues until either the queue is exhausted or the target cell is reached. If the queue is empty and the target hasn't been visited, it means there's no valid path, so we return -1. Key insights from this approach include the BFS guarantee of finding the shortest path due to its level order exploration and the use of the visited set to avoid redundant computations. Additionally, the direction array simplifies the traversal logic, ensuring all valid movements are considered. These elements work together to make the algorithm both efficient and easy to implement. The algorithm relies on 3 primary data structures: the queue, the visited set, and the direction array. The queue is central to BFS, enabling level-order traversal by storing the current cell and its associated path length. The visited set ensures that each cell is processed only once, preventing cycles and redundant work. Finally, the direction array encodes all 8 possible movements, simplifying the code and ensuring all directions are explored uniformly. Now let's analyze the time and space complexity. The time complexity is O(n squared), where n is the size of the grid. This is because each cell can be processed at most once, and for each cell, we check a constant number of neighbors up to 8. The space complexity is also O(n squared), in the worst case, as we may need to store all n(2) cells in the visited set in the queue. It's also important to consider edge cases. These include situations like an empty grid, invalid start or end points, or grids where all cells are open or blocked. Another edge case is when the start and end points are the same, such as in a 1x1 grid where the single cell is open. Finally, there are cases where obstacles require the algorithm to navigate around them to find a valid path. For example, let's consider a sample grid, 010, 001, 100. This input will help demonstrate how the algorithm handles a realistic scenario. In the example grid provided, the algorithm starts at 00 with a path length of 1. From there, it explores all 8 possible directions and enqueues valid cells. The first enqueued cells are 10 and 11, both with a path length of 2. As BFS continues, it processes these cells, exploring their neighbors and adding valid ones to the queue. This process progresses level by level, ensuring that each cell is visited at the shortest possible distance from the start. Eventually, the algorithm reaches the target cell, 22, with a path length of 4. Since this is the first time the target is reached, we know it's the shortest path. The algorithm then terminates and returns 4 as the final output. This example illustrates how BFS systematically explores the grid to find the shortest path while avoiding obstacles and redundant processing. To solve the problem of finding the shortest path in a binary matrix, we start by importing the DEET class from the Collections module for efficient queue management during our breadth-first search, or BFS. Next, we define our solution class and the method shortest-path binary matrix, which takes the binary grid as input. The first step is to determine the size of the grid, stored in the variable n. Now, an important edge case is handled up front. If the starting cell at the top left corner or the ending cell at the bottom right corner is blocked, meaning their value is not 0, we immediately return -1 since no path is possible. We then define the possible directions of movement, which include 8 directions to account for diagonal moves along with horizontal and vertical ones. This is stored as a list of tuples representing the changes in row and column indices. To initiate the BFS, we use a queue that starts with the top left cell, represented as a tuple containing its coordinates and an initial distance of 1. At the same time, we mark this starting cell as visited by setting its value in the grid to 1. Entering the BFS loop, we repeatedly remove elements from the front of the queue. For each cell we process, we first check if we have reached the bottom right corner. If so, the current distance is returned as the length of the shortest path. If the bottom right corner has not been reached, we proceed to explore all possible movements from the current cell. Using the 8 directions defined earlier, we calculate the new row and column indices for each potential move. Before considering a move valid, we ensure the new position is within the grid boundaries and that the cell has not been visited yet, as indicated by its value being 0. If these conditions are satisfied, we add the new position to the queue along with the updated path length, and we mark the cell as visited by setting its value to 1. This ensures we do not process the same cell multiple times, which helps maintain efficiency and prevents infinite loops. The BFS loop continues until the queue is empty, meaning all reachable cells have been explored. If no path to the bottom right corner is found after exhausting the queue, we return -1 to indicate that it is impossible to reach the destination. This ensures that the function properly handles cases where no valid path exists in the binary matrix. Here, we start by importing necessary utilities and defining the shortest path binary matrix method. The function accepts a 2D grid as input, where each cell represents either an open path, 0, or a blocked path, 1. The first step is to retrieve the size of the grid, which is stored in the variable n. Next, we handle an edge case. If either the starting cell at the top left corner or the ending cell at the bottom right corner is blocked, there's no valid path, so we immediately return -1. To facilitate movement in all 8 possible directions, such as up, down, diagonals, and so on, we define a directions array. Then, we initialize a breadth-first search, BFS, using a queue. Each element in the queue represents the current cell's coordinates and the distance traveled so far. The starting cell, at position 0, 0, is marked as visited by setting its value in the grid to 1, ensuring we don't revisit it. The BFS loop begins by polling the front of the queue to process the current cell. If the current cell's coordinates match the bottom right corner, it means we've successfully found the shortest path, so we return the accumulated distance. Otherwise, we proceed to explore all 8 possible directions using the directions array. For each direction, we calculate the new coordinates and check if the position is within bounds and hasn't been visited yet. If these conditions are met, we add the new position to the queue, along with the updated distance, and mark the cell as visited by setting its value in the grid to 1. This process repeats until the queue is empty. If we exhaust all possibilities without reaching the bottom right corner, it means no valid path exists. In such a case, we return -1 to indicate failure. This approach ensures that we explore the shortest path first due to the nature of BFS, making it an optimal solution for this problem. To solve this problem, we use the breadth-first search, or BFS, algorithm to find the shortest path in a binary matrix. In this example, we start with a 3x3 grid. The initial setup involves determining the size of the grid, which is 3, and checking the values of the top left and bottom right cells. Both are unblocked, so we proceed. We define the 8 possible movement directions for navigating through the grid. Then, we initialize our BFS queue with the starting position, 0, 0, and a path length of 1. At the same time, we mark the starting cell as visited by setting its value to 1. This ensures we don't revisit it during our search. The algorithm then begins its iterative process of exploring the grid cell by cell. We dequeue the first element, which is 0, 0, 1, representing the current position and path length. From this position, we check all 8 possible directions. Some directions, like 0, 1, and 1, 0, lead to blocked cells, so we skip them. However, 1, 1 is valid and unvisited, so we add it to the queue with an updated path length of 2 and mark it as visited. Now the queue contains 1, 1, 2. In the next step, we dequeue 1, 1, 2, and explore its neighbors. This time, 2, 2 is valid and unvisited, so we add it to the queue with a path length of 3 and mark it as visited. Finally, we dequeue 2, 2, 3, and realize we've reached the target cell. Since the path length is 3, that's our output. In this second example, we use the same BFS approach, but this time no path exists through the grid. The grid is initialized as a 3x3 matrix, and we start with the same setup. The grid size is 3, and the top left and bottom right cells are unblocked, so BFS begins. The queue is initialized with 0, 0, 1, and we mark the starting cell as visited. We then dequeue 0, 0, 1 to explore its neighbors. From 0, 0, we check all 8 possible directions. Unfortunately, every direction leads to a blocked cell. For example, 0, 1, and 1, 0 are both blocked, and the same holds true for the other directions. Since no valid moves are available, the queue becomes empty. At this point, the BFS algorithm terminates because there are no more cells to explore. As a result, no path to the target cell, 2, 2, was found, and the output is -1. In the third example, we have a single-cell grid, which is the simplest case. The grid size is 1. We start by checking if the only cell in the grid is blocked. It's not, so BFS begins. The queue is initialized with 0, 0, 1 representing the starting position and path length. We immediately dequeue 0, 0, 1 and find that we're already at the target cell. Since we reached the target in one step, the output is 1. This example highlights the efficiency of BFS. The shortest path is found immediately when there's only one cell. Marking cells as visited and exploring layer by layer ensures we avoid infinite loops or redundant computations. One key takeaway from this algorithm is that if the BFS queue is exhausted without reaching the target cell, it means there is no valid path through the grid. In such cases, we return -1. This ensures the algorithm correctly handles cases where no solution exists, providing a clear and consistent output. The time complexity of this solution is n squared, where n represents the size of the grid, which is n by n. To understand this, first consider that the algorithm processes the entire grid. Since there are n squared cells in an nxn grid, this forms the baseline for our time complexity. Next, we use breadth-first search, or BFS, to explore the grid. BFS ensures that each cell is visited only once during the traversal. Even though we check up to 8 neighbors for each cell, these neighbor checks do not increase the overall complexity because each cell's neighbors are explored only once when the cell itself is processed. Therefore, whether we're visiting a cell or checking its neighbors, the number of operations remains proportional to the total number of cells, which is n squared. This makes the dominant factor the BFS traversal, resulting in an overall time complexity of n squared. The space complexity of this solution is also n squared, and here's why. First, consider the BFS queue, which holds the cells to be processed. In the worst case, when most or all cells in the grid are traversable, the queue can grow up to n squared in size, as it may temporarily store all the cells in the grid. Next, the input grid is modified in place to mark cells as visited, meaning no additional space is allocated for a separate visited array. This optimization helps reduce memory usage. Finally, the algorithm uses a small, fixed list of 8 directions to handle movement, which requires constant space, or O1. Since the queue dominates the space usage in the worst case, the overall space complexity is n squared. Now let's analyze the best, average, and worst case scenarios for this algorithm. In the best case, the start and end cells are connected by a direct, clear path. While BFS will terminate early in this situation, the theoretical time complexity remains n squared, since it depends on the grid size, though fewer operations are performed in practice. In the average case, BFS explores a portion of the grid proportional to the shortest path length before finding the target. However, the worst-case complexity still applies here because it depends on the grid size rather than the specific path. Lastly, in the worst case, when all cells are traversable, the algorithm must process all n-squared cells. For comparison, brute force approaches would attempt to enumerate all possible paths, leading to exponential time complexity, n squared, which grows far faster than the n squared complexity of BFS. This highlights the efficiency of the BFS approach. BFS is optimal for this problem because it guarantees the shortest path in an unweighted grid. This is achieved by exploring all cells at the current distance before moving on to cells at the next distance level. Additionally, marking cells as visited prevents redundant computations, ensuring that each cell is processed only once. To confirm the time complexity mathematically, note that the BFS queue processes each of the n-squared cells at most once, making the total number of operations proportional to n-squared. Neighbor exploration is limited to 8 directions per cell, adding only a constant factor to the time complexity, which simplifies to n squared. As for space complexity, the queue size can grow to n squared, in the worst case, dominating the overall space usage. Both time and space complexities are therefore n squared, making BFS both efficient and well-suited for this problem. When solving grid-based problems like this one, there are several common mistakes to watch out for. First, not handling edge cases is a frequent pitfall. For example, you might encounter an empty grid, a single-element grid, or scenarios where obstacles block all possible paths. Always take the time to analyze constraints and test for these boundary conditions to ensure robustness. Another issue is using inefficient recursion without memoization. For problems with overlapping subproblems, plain recursion can lead to exponential time complexity, which is highly inefficient. Instead, optimize your solution with memoization or dynamic programming. Similarly, incorrect base cases in recursion can cause major issues. If you forget to account for conditions like going out of bounds or encountering obstacles, your code may fall into infinite recursion or produce incorrect results. Additionally, numeric overflow is something to be mindful of, especially in languages like Java or C++ where large grids and operations involving summation or modulo arithmetic can lead to unexpected errors. Finally, relying solely on brute force methods during interviews might give you correct results for small inputs, but it won't scale for larger grids. Always evaluate the time complexity of your solution and prioritize efficient approaches upfront. Now let's consider some key insights that can help during interviews. First, developing strong pattern recognition is essential. Many grid problems fall into categories like dynamic programming, backtracking, or graph traversal using DFS or BFS. Identifying these patterns quickly allows you to pinpoint the most suitable approach. Space optimization is another important aspect to consider. For instance, in dynamic programming problems, a 2D DP table can often be optimized down to a 1D array if only the previous row's values are needed. Analyzing constraints is equally critical. If the grid size is small, such as n being less than or equal to 10, brute force methods like backtracking or recursion might be efficient enough. However, if the input size grows, you'll need to shift to more scalable techniques. Another key point is explaining trade-offs in your approach. If you switch from brute force to dynamic programming or another method, ensure you clearly articulate the differences in time and space complexity. This demonstrates a thoughtful problem-solving process. To reinforce these concepts, it's helpful to practice related problems such as unique paths, minimum path sum, or number of islands. Each of these involves variations of grid traversal or dynamic programming, giving you a solid foundation for tackling similar challenges. Finally, let's explore some alternative approaches to solving these problems. Brute force using DFS is a straightforward method where you recursively explore all possible paths. While it's simple to implement, its exponential time complexity makes it impractical for larger grids, though it can be useful for understanding the problem on small inputs. Dynamic programming is a more efficient alternative, where you use a 2D DP table to store the results of subproblems. This approach has a time complexity of m*n, and can often be optimized in terms of space, reducing the need for a full 2D table to just a single row. Breadth first search, or BFS, is another powerful method, particularly for shortest path problems. Since BFS explores layer by layer, it's optimal for unweighted grids and ensures the shortest path is found. For problems with additional constraints, like visiting all cells exactly once, backtracking can be an effective approach. This involves exploring all valid configurations while adhering to the constraints. Each method has its own trade-offs in terms of readability, efficiency, and adaptability to the problem's requirements, so it's important to choose the approach that best aligns with the specific constraints and goals of the problem you're tackling. Thank you for following along. We summarized the key approaches and complexities for solving this problem. Remember to practice BFS and similar graph traversal problems to strengthen your skills. If you enjoyed this, make sure to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!